Hello, so last video we were looking at the base graphs of sine, cosine and tan, and now we're going to have a look at what happens when we apply transformations. So just as a reminder, looking at slide 16 here, we've got the three categories of transformations are reflections, dilations and translations. And don't forget that you can have reflections of the input and reflections of the output, dilations of the input, dilations of the output, and translations of the input and output as well. So there's three categories, and they each apply either to the input or to the output. And of course, you can combine them all. For trig functions, this is all of these apply for trig functions, but for Maths Methods Foundation, we're just going to be looking at reflections and we're going to be looking at dilations, and we are not required to look at translations. Okay, so we won't be adding K or subtracting H, just reflections and dilations. So let's have a look at what they do to the graph. We should know by now what a reflection is. It's when we reflect about the x-axis or about the y-axis, and we do so by making the input or the output negative. Now this is negative tan of x, so we are taking tan of x, the original graph, and we are making each output value negative. So if it was positive, it would be negative, and if it were negative, it would be positive. So going back to our function here is our tan graph, and I might even just make this between 0 and 2 pi, just so we can sort of see it in action a little bit more carefully, I suppose. Okay, so that's what tan looks like. It goes up to infinity here, and it starts down here. So what would negative tan look like? Please feel free to pause the video and think about it, or just think about it in your head. There we go. So it is literally just flipped. Okay, so this bit goes down here. This bit that was negative is now positive. This bit which was positive is now negative, and so on. So I'll put the negative there, and you can see it's flipped over. Similarly, the cosine graph, have a think about it. This is what it looks like. I might even do the same thing again, just so that we can concentrate on the base graph, I suppose. So what would it look like flipped? It would look a little bit like that. And what would sine look like flipped? Have a think about it. It would look a little bit like that. Okay, so they're all flipped. So I've just done a couple here just to get our thoughts going here. So if I was graphing this, I know that it's basically the same points and everything. It's just a matter of drawing it upside down effectively. So there's my first one, which is pi on 2. I'm just drawing in my asymptotes. Then I'm going to have pi here for the middle, and then I'm going to have another asymptote, which is pi length along, so that's 3 pi on 2. And then I'm going to have 4 pi on 2 here, which is going to, or 2 pi in other words, here. But instead of doing this, which is how I normally start, I'm just going to draw it going down like so. And then it's going to be like this, and then it's going to be like this, and then it's going to be like, try that again. Going to be like this. And I'm done. Okay, so that's how I do that one. Cosine, I would probably just freestyle it a bit more. So I would go, it normally does this, down, up, and down. So I just got to reverse that. So I'm going to go like this, then like this, and then like this, like so. And then I'm going to put in my intervals. So 2 pi and pi, split it again, pi on 2 and 3 pi on 2. And we're done. And I won't do sine, but you get a sense of what needs to be done there. So that's basically reflections done. Next one is dilations, and I'm going to split dilations into two. We're going to talk about vertical dilations and horizontal dilations. So let's have a look at them first. You can see I've got some examples here to draw, but just to remind you that a vertical dilation means it's either stretched this way or shrunk this way. And I'm just trying to use language which is actually a little bit more in line with how your information sheet says it for maths methods. And this is the way it would describe it: a dilation by a factor something, or some sort of factor, in the direction or in the same direction as the y-axis. I think it might actually say in direction of y-axis. So you can see that it's parallel to the y-axis, this dilation. It's going either stretchy or compressy here. Okay, so let's just have a look. I just thought, see what it does first. We'll stick with sine just for the sake of it. So I'll move it sine back to positive, so we're not doing too many things at once. Again, feel free to just stop for a moment and try it for yourself. I'm going to put a 2 in front of sine of x. What do you think it's going to happen to the graph? Okay, did you think this? I should have asked you to pause the video. I meant to. Notice that the x-intercepts 0, pi, and 2 pi stay there. They are anchored, because when I stretch a 0, it's going to stay at 0. So that's why they're anchored at the zeros. But every other value has doubled in its size, which means the maximum, which was 1, has now stretched to 2. And the minimum, which was -1, is now stretched to -2. And so effectively, we have stretched the overall height of this function. Now, you might recall from a previous video that the height of a function is called the amplitude, okay? So the dilation, the vertical dilation factor, is in fact what we call the amplitude of the function. I'll talk about that in just a few moments. And then there's also half x as well. So if I go 1 over 2, we can see that everything has been compressed. The x-intercepts stay the same, 0, pi, 2 pi. But instead of stretching another way up to 1, it's now gone just down to a half. And what was -1 is now down to -1/2. Everything has been compressed, squished by a factor of a half. Okay, so if I was drawing this for real, I would certainly just draw my axes in. Again, I'm just using 0 to 2 pi. It's not always. And I would then draw my graph in. And you might notice when I do this that I'm actually just going to draw it like I normally do. Okay, just the same old graph. My intercepts haven't changed, so I'll reflect that as well. Hat 2 pi, split it to pi, split it again to pi on 2, split it on this end to make it 3 pi on 2. Done. This is the bit that changes. My maximum and minimum is now 2 and -2. So 2, -2, and there's the 2 there. Similarly, for this one here, I draw my axes, y, x. Draw my graph in, like so. 2 pi, split it to make pi, split it to make pi on 2, split it to make 3 pi on 2, put in my maximum minimum, which is going to be a half to a -1/2, and I'm done. So just to summarize with that, vertical dilation is what we've looked at there, and the vertical dilation is equal to what we call the amplitude of the function. Amplitude only works for sine and cosine. We don't talk about amplitude for tan because there is no maximum minimum. If I tick this, here's my tan graph. If I make it double, so that's what a tan graph normally looks like. If I double it, it's definitely changing, isn't it? It's accelerating faster, so it's stretching much more quickly. The asymptotes are still the same, still going towards the asymptotes. It's just that this is a lot more steeper. So when you're sketching, you can't really tell. You know, you can sort of draw it, but without any other relative points, it kind of pretty much looks the same. So talking about amplitude doesn't make sense in terms of a height anyway, but nor is it something that's worthwhile sketching in, I suppose. Okay, so it's not that tan can't have a vertical dilation, it's just that it's not a great sketch. Okay, so an amplitude is good for sine, good for cosine. And in terms of calculating the amplitude, I think I said this before, so just to remind you, what I'm really doing is I'm looking at the height between the maximum and the minimum. So in this instance, there's a height of 1 between here and here, and then I halve it to get a half. Note that if I make it negative 2 cos x, like this one here, this has an amplitude of 2 because it goes from 2 to negative 2. So that's a total length of 4, which means that the amplitude is 2. So it has an amplitude of 2, not an amplitude of negative 2. So that number there denotes that a reflection has happened, plus there has been an amplitude change. Hope that makes sense. Okay, let's have a look at horizontal dilation. This has an interesting effect too. You can see from our usual understanding of horizontal dilation, there is a horizontal stretch or a horizontal compression. Okay, it gets squishier or it gets extended. And we would say this is a dilation by a factor in the same direction of the x-axis. Okay, so it stretches that way. So you can see that this is an input. Sorry, I wrote output there, but I meant input. This is an input effect. And because it's an input effect, we are changing the usual input, which is x, to something else, in this case 2x. And then the second example is half x. And I've also got a tan one as well. Tan is useful in this instance here. Let's see what it happens. So let's do the first one, which is y equals sine of 2x. And can you see what happened there? Over 0 to 2 pi, I now have 2 cycles of the sine wave. So putting in 2, in fact, shortened the period. Okay, instead of, it's repeated twice over 2 pi, which means there's a compression happening. Okay, so it's squishing this way, and because it's compressing, it changes the period. So the period is now twice. Okay, so if I were drawing that, I would draw my axis in. Oops, like so. I would start splitting again. That's where my first cycle finishes, pi. So because, might just do it better in the middle there. There we go. So because this is my one cycle, I'm going to do the same thing again, but I've got to do it more often, I suppose. This is the hard one to do, I suppose. I might even zoom up so you can see it, see just this. So in this one cycle here, from here to here, half of it is pi on 2. Oh, hang on. Sorry, I'll draw it first. Sorry. I'll just draw it first. So I'm going to have like so, and then I'm going to repeat it again. Okay, so I've got my 2 repeats in there. Now, in terms of working out the critical points, half of pi is pi on 2, so that's that bit there. Between pi on 2 and pi on 4 is what? Well, pi on 2 and pi, well, pi can be written as 2 pi on 2, so that's okay. Now I need a number in between, but I'm not too sure what that would be because this is 1 pi and 2 pi. So what I do is I split them a little bit more. You can do this in your head after a while, don't worry. So pi on 2 is 2 pi on 4, and 2 pi on 2 is 4 pi on 4. And now I can see I've got a 3 pi on 4 in between. Like so. So here is 3 pi on 4. If you sort of ignore the pi, you should have enough fraction knowledge to understand that. Between a half and 1 is 3/4. So ignoring the pi, we've got 1/2, we've got 1. What's the halfway point between a half and 1? 3/4. Similarly here, we're going to have 1/4 or pi on 4. So there's the first bit done. Then we've got to do the same thing with the next bit, and that's a little bit harder, I suppose. So again, ignoring the pi, if I said to you, what's between pi and 2 pi? It's 1.5, right? So that's 3 pi on 2. So there's our midpoint there. But now I have to work out what's between here and here as well. And I could do a similar sort of logic. I could say, what's between 1 and 1.5? Well, it would be 1 1/4, wouldn't it? So that's 4 pi on 3. Or, oops, wrong way around, sorry. 5 pi on 4. And what's between 1.5 and 2? It's 1 3/4. So 1 3/4 is 7 pi on 4. And there we're done. So there's a bit of fraction work there, so it's probably important that you revise that if you need to. Now, like I said, if you can either think of it visually like this, like, in quarters and halves, or you can sort of use this kind of logic up here to try and work out the middle point, whatever floats your boat. But yeah, you do need to spend some time with fractions. This is, believe it or not, even though there's a fraction here, it's actually easier to work out. If I go to Desmos and put in a half into the cos, maybe you could think about what it would do. What have we got? It's weird, isn't it? Just a little wavy line like this. And that's because all the cosine values have now been, all the x values have now been halved before they go into the cosine. So it basically slows down the making of this graph. So really, in order to see it, I'm going to have to go to 4 pi to get a full cycle in. That's only half a cycle. So it's that tulip shape again, but it's been stretched over 4 pi instead of 2 pi. So that's actually easier to graph, believe it or not, because now I can just sort of do this. And I can use the same logic as before. I'm just going to draw my tulip, make it as even as possible, unlike me. But I'm just going to use 4 pi as my endpoint, and away I go. Halve it to make 2 pi. Half of 2 pi is pi. Half of between 2 pi and 4 pi is 3 pi. And that's it. That's all I need to know. I should have put maximum and minute in as well. So that should have been 1 and -1 on my y-axis as well, which I forgot about. And that's basically it. Y equals tan 2x is a little bit trickier to see, so let's go have a look. So I'll turn that off, turn this on. Y equals 2 tan x. And it's repeated quite a few times. So the asymptotes are halved. So instead of being on pi on 2, it's now pi on 4. And instead of 3 pi on 2, it's going to be 3 pi on 4 to get those asymptotes in. Everything's been squished, you see. So I might even change the domain of this as well to just pi, because the period is now pi on 2, right? From here to here, it's a pi on 2 value. It's been halved from pi to pi on 2. So yeah, it's a bit trickier, I suppose, in a sense. So in terms of graphing it, same sort of deal. There's my axes. Put my asymptotes in first. My asymptotes are at pi on 4 now. So I can still stretch it out a little bit anyway, but it's just a matter of doing the labels. And then 2 lots of pi on 4 is pi on 2. Like so. Then I've got another little one here. I might need more, I can't quite think. This is between 0 and pi this time. So what was 1 cycle, it's now 2 cycles long. So my graph is going to be zooming up to pi on 4 here, and then it's going to be coming to the midpoint and then going up like that, and then that's going to be repeated like so, and we can keep going if we wanted to. So just labeling that, I'm going to zoom up so you can sort of see just the tan graph there. We're going to have pi on 4, then we're going to have pi on 2, then we're going to have 3/4 of pi here, and so I do need a bit more, don't I? So I'm going to have this to 2 pi, to pi, sorry, like so. Okay, so then we can work out what these middle points are. So it's always midpoint. So what's between pi on 4? What's between 1/4 and 1/2? 3/8, is it? So I can put 3 pi on 8. And what's between 1/2 and 3/4? 5/8. So it'll be 5 pi on 8. So the fraction knowledge is a bit scary, but you can get there. And again, if you prefer, you can say, I need to know the midpoint between pi on 4 and pi on 2. What's that? Well, make them all over 8 instead. So pi on, so 2 pi on 8, and we've got, oh, sorry, I went too far then. Try that again. So between pi on 4 and pi on 2, that would be pi on 4 and 2 pi on 4, but that's no good for us because there's nothing between, there's no whole number between 1 and 2. So I'll double it again to get 2 pi on 4 and 4 pi on, on 8, and 4 pi on 8, and now we can see it's 3 pi on 8. So you could do it that way instead if you like, if your fraction knowledge is a bit weak, but I get that the fraction knowledge is probably the thing that's going to be harder here. If it's in degrees, it's much easier to halve as you go along. Technically, you could just work with decimals here as well. I don't know if it makes it easier in a non-calculator section to be talking about what 3/8 is as a decimal, but you can if that's easier for you. Okay, so that's basically the horizontal dilations. We're just going to finish up by talking about that in a bit more detail in the summary, and then I'm going to put the rest of this in a separate video because this one's been going on long enough. So the horizontal dilation is basically what we talk about in relation to period. So hopefully you've seen that now, that the that value affects the period. So if it's a big number, it means that the period is shortened, and if it's a small number fraction, then it means the period is lengthened. Do note that we don't bother with a negative reflection of the input, so we don't ever bother about negative x. Okay, so in summary, and this will finish off for this video, in summary, we have y equals a sine of bx, a cos of bx, or y equals tan bx. Don't worry about the a. So in summary, if you see the value a, then that affects the period. If there's a value for b, then that affects, oops, that was bad of me, wasn't it? Exactly wrong. If you see a, that affects the amplitude. And if you see B, that affects the period. And that will do us for today. Once I can spell. Okay, that's it.